Hello everyone, welcome back to Reverse Engineering Linux 32-bit applications. In this video, we're going to continue our discussion of format string errors, and in particular, we're going to talk about getting stack data. So how can we do this? In a previous video, we had talked about getting programs to crash. We talked a little bit about format strings, and we examined this very simple program right here that had a format string flaw. So in this video, we're going to start out by looking at this again, and I want to talk about how can I examine the stack. And it's actually very easy to do. So if I take my executable and I run it, and I will give it something very simple, %x, 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 %x. This will give me some output from the user. So this will output 4 values, 4 32-bit values from the stack. Now we said last time when we did this, we ran this through immunity. Actually not immunity, Evans debugger, which is equivalent to immunity on the Linux platform. And we noticed the results. We said, hey, these look kind of like addresses, and these addresses just so happen to look like addresses on the stack because they were. And you would also notice that this address right here looked an awful lot like an address for an instruction in our program. We said that our programs typically start at 0804 and then something else for the rest of the bytes. So that's kind of what we see here in this case. Now, if I were to take this program again and let me run it with the same arguments, however, going to run it through EDB. I'll go ahead and go to my breakpoint, analyze, and I'm going to go right up to this printf. So I'll go ahead and step. Okay, so I'm ready to call printf. So in this case, notice what these first 4 entries should be. This first one is a pointer to this string, %x, 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 which is on the stack at FFE2 3227. So if I were to scroll down, I would see it. Then I have something else that also looks like an address on the stack. Something that, once again, looks like a stack address. And then here I have a return, and it says this is return to this from this call. So it's giving me a little bit of information there from libc blah 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 blah. Right, so it's telling me all about that call. So that is the kind of information I can get from my stack. And you might be thinking, yeah, so what? So I can get information from the stack. Well, if I had a slightly more complicated program, this information is potentially a little bit more interesting. So let's go ahead and make some very small changes to our program. I'm going to save this as format2.c. And now I'm going to do this. I'm going to create a new function, int func1, and it will take a string. And this is going to do printf. And it's going to say printf on the string that you passed in. Then I'll return 0. Keep it nice and simple. And then I will have another function. I will call it password is valid. And I'll do some sort of check. I'll say if stir comp. And I probably shouldn't be using string here. Yes, it'll work in C, but you know, it's just not a good habit to be in. So I'll just say the string. So I'm going to compare this, and of course I will hard code a password, which is really, really bad. This doesn't really matter. I'm just trying to prove a point here as to how this is going to work. All right, so here in my program, instead of calling printf directly, I'm going to do this. I'm going to call password is valid. And I'm also going to do something like this before I return. So now I'm going to have to use curly brackets. I'm going to make a call to func1 with password. And I don't really need the brackets in the second case here, but personally I don't like to have it kind of unbalanced, if you will. Okay, so now I'm changing this, and again, instead of calling printf directly, I'm going to call password is valid, which will call printf in this case. In the case of this being valid. So yes, this is kind of a contrived example, obviously something that prints out your password if this was in fact the case. In fact, I won't print out the password here. I will instead print, well, you know what, I will print the password. Just because I want to show you this particular technique that might be useful if you find a program with this kind of a flaw. So I'm going to say password is valid. All right, so let me go ahead and save this. And let me build it. I can close this because I don't need that at the moment. GCC-M32 format2.c, and we'll output this as formatString2. And I got a warning: format not a string literal, no format arguments given. Implicit declaration of func stir comp. Let me include string.h. And now I have just the one warning remaining, and we talked about this warning before. We said that Linux and GCC are smart enough and nice enough to warn you that, hey, you're doing something that's not terribly smart right here. All right, so let's do this. Let's go ahead and do the following. I'm going to run this program. And actually, I'm going to make one small change to this program. And that small change is this. I'm going to add another parameter here. And this actually makes a little bit more sense as well. The reason for that, of course, is I will never have a valid password unless I make this particular change. And so now I'm going to run this. Well, first I'm going to build it. And now I'm going to run it. Go ahead and do my usual analysis. All right, so I will put a breakpoint right here. And I should have some output. This program prints what the user inputs. You'll notice that it changed my call to print from printf to puts, which is fine. Okay, so now I'm about ready to call password is valid. And we'll see what's going to happen when I do this. So I'm going to trace into this. I'm doing the stir compare. And in this case, I'm going to call func1. So I'm calling func1. And I'm ready to call printf. So here's what I have. I have my stack, and I have a bunch of values here on the stack. And some of these values could be interesting to me. So let me go ahead and step forward. And now I've done my print. And it says this exited normally. All right, and here's what I printed out. I printed out just a few of these values once again. Now, I just printed out a few items, and I could print out a lot more than this. I could print out more than just a few things. So what this will allow me to do is the more I print out, the more I will go backward in time on my stack. So I will eventually get two things that belong to other calls. So here's what I mean by that. Let me run this again, but now I'm going to go a little crazy. Now, I could have gotten crazier than this, but I didn't. So let me go ahead and proceed here. So I'm going to go to my first breakpoint and do my normal analysis. Step into my password is valid method. This is going to call func1. and func1 is going to print out a ton of entries from my stack. So I'll go ahead and step here, and I'm just going to let it run to completion. We'll have a look at the output. All right, so here's my output once again. So I've been able to get more and more information off of the stack. Now, there's a couple of things I can do with this information. I can get addresses for returning from function calls. So if I look at the code and I find where this flaw exists, I might be able to say, oh, there's a return address for a particular function. I can use that information as part of another attack. For example, if I'm using ASLR, which I probably am, I can say, oh, this function call, which is located in this library, was at this address. Now I know where it is because the start of each library is randomized. However, the offset is not. It's going to be the same for every similar version of that library. Everything, let's say it's libc. Everything for that version of libc, it's going to be located in the same place. So that is going to allow me to locate other functions. So I can use the information that's been leaked here in order to do that. Other things that I can do. I can use what I've leaked here in order to find out what's being passed to some of these other functions. So here I have this password that's being passed. Now, just to make it easier to see, I'm going to change this password to A. So that is A days. So I want to be able to locate this on my stack. I'm going to go ahead and save this program, and I'm going to rebuild it. Once again, I have that same warning. And let me run it. Run it to my breakpoint. And step away. So here I have my location of my A's. And then I go forward. Now, in this case, I didn't get something terribly interesting for a couple of reasons. because I hard-coded this, my pointer to my A's is in my program. Now, what would be more likely to happen is that the pointer to this would be somewhere on my stack instead. So how could I get that to happen? Well, I could use something like gets in order to get input from the user. But that's too much like work. So let's see if we can cheat a little bit here. And we're going to try to fake it. And we'll just give it a second parameter. I'm going to save that. I'm going to rebuild it. Run EDB on it. And actually, this is not going to be happy because I forgot to give that second parameter. And so it basically did nothing. Let me fix that. So now we're almost in business. Except it looks like I must have a typo somewhere. Because I don't think it printed out my stuff. So yeah, I must have a little typo. Let's have a look at this. 1, 2, 3, 4, 5, 6, 7, 8. And that's my second argument. Just to make my life easier, I am going to do this in both cases. That way I don't have to worry about any weird typos or anything. And now I'm getting ready to call func1. Go ahead and trace into that. And we're getting ready to call printf. Go ahead and hit F9. And it says this executed normally. So what do we see here? We see that we have more and more of our stack that's been printed, but guess what? We haven't quite printed enough yet to get all the way to those A's. It seems like we've printed a lot, but we haven't quite made it there yet. So with a little experimentation, I could get more and more of the stack that I could read, and that would allow me to leak information. And again, as I said before, leaking addresses can help you find out where things are in memory if you're using ASLR, and you might also be able to leak things like passwords or other sensitive information that are being passed around. All right, so one other thing I wanted to show you when it comes to leaking information. If I wanted to get like the 500th item off of my stack, maybe the 512th item off of my stack, I could print %x, %x, %x an awful lot of times. That's probably not what I want to do though. Fortunately, there is a shortcut. And the shortcut looks kind of like this. I can say, please go to item 512 $X. And this is just a little shorthand. And in this case, I'm not even going to run this through EDB. I just want to show you how this works. And there wasn't a 512th item, but let me go ahead and do this with something a little smaller. Say 2. This one seems a little bit unhappy with me. Of course. I should have used single quotes. That's my bad. Remember, if you use single quotes, that says, hey, Linux, please do not interpret this. So when I used double quotes, %2 or %512 got interpreted on me. So once again, I could say 512, and it's going to give me that item, which happens to be just a 0 in this case. So you can arbitrarily get items off of the stack. So this is kind of a big deal. You could leak information of all sorts if you have a format string vulnerability in your program. So this is another way you can abuse a program that has this problem. Now in some future videos, we will talk about ways that you can abuse a program that has format string vulnerabilities. But that's all that I had for this video. As a reminder, this video is one in a series of videos and courses that we have here at Pentester Academy, your source for all things InfoSec. And I look forward to seeing you again in this course or another course soon. See you then.